How you doing? I am here to help you through the week 3 catalyst. So pull it up, pull this up. Let's do it together. Remember, this is an agency grade. All this stuff is on your exam, so why not get 100 right now? Let's go. So on that week 3 catalyst, number 1 says, which of the following graphs best represents an object moving in the positive direction at a constant speed? Okay, so I've got a graph and a series of graphs, and I've got to pick the one that shows it going in a positive direction at a constant speed. So it's important to look at these graphs, and I can see that they're all on the xy axis, distance versus time graphs, right? So we're looking at kinematic graphs, distance versus time graphs, and I'm going to set mine up. This is how you would draw yours, just the same as they've got it on here. So we've got distance or displacement with respect to time, d over t. Hey, and remember, velocity is d over t. So guess what the slope of this line is going to be? The velocity, right? So what would a constant velocity look like? Well, time we think about in seconds, right? As seconds go on, in like that's 1 second, 2 second, 3 second, 4 second, and here's 0. That's the origin. The displacement is going to go up, right? So here I have 1 meter, 2 meter, and we measure displacement in meters, right? Meters per second. Wow. Meters per second. Meters over second. 3, 4, so on and so forth. So what does it mean to have a constant velocity, right? The velocity is constant, which means as time goes on, the distance increases the same each time. So let's do 1 meter per second, right? So after 1 second, you've gone 1 meter. After 2 seconds, you've gone another meter. After 3 seconds, you've gone another meter. After 4 seconds, you've gone, and so on and so forth. And this will produce a graph for you, and that graph should look like this. It should be a straight line, right? A straight line. And the slope of this graph is going to tell you the velocity, right? It's going to tell you the velocity. It's not always 1 meter a second. It could be 2 meters a second, right? So let's say that in 1 second you went 2 meters. And in 2 seconds you would have went 4 meters. And in 3 seconds you would have went 6 meters. And in 4 seconds you would have went 8, so on and so forth. And guess what that produces? Another line. Yeah. Right? So these are all in the positive direction, which means I'm going away from the origin, but the starting point. This one just happens to be a little bit faster than this one, a faster velocity, because it goes further in a less amount of time, right? You can contrast this with something that doesn't move at a constant velocity. Let's say maybe it speeds up. What if it speeds up? And I'll do this in this color right here. So let's say I'm going real slow, right? So after 2 seconds, I've only gone 1 meter. And at 3 seconds, I've only gone 1.5 meters. But I start to speed up rapidly, right? I speed up. You can see that I'm changing my slope. I'm bending it up. This we call acceleration. Acceleration. Right here, right? And conversely, we can also accelerate in the negative direction, down that way. Let's say I'm going pretty fast like this, but I start to slow down, and that is called deceleration right there, deceleration. So you're going to see these even after we get back from Christmas on your test. You need to know how to do them, right? So pick the graph that best depicts an object moving in a positive direction at a constant speed. You're going to have to do that. All right, number 2. It says a car is traveling at 21 meters a second, and it slows to a stop at a constant rate over 5 seconds. How far does the car travel during these 5 seconds before it stops? Okay, so let's get rid of this. We're on question number 2. It looks like a kinematic equation, right? A car is traveling at 21 meters a second. What does that tell you? A car is traveling at 21 meters a second, right? So I'm going to draw my car here. It's traveling at 21 meters per second. Why can't I ever do this right? It's traveling at 21 meters per second. So here's my car. And it's traveling at 21 meters per second. Well, that would be its initial velocity, as we say, right? Initially, it's going 21 meters a second. Let's see what else happens. It slows to a stop at a constant rate over 5 seconds. It slows to a stop. So after 5 seconds, right? After time 5 seconds, it's going to slow to a stop. What is its final velocity? You should see that it is 0, right? So its initial velocity is 21. Its final velocity is 0, right? And it says, how far does the car travel during those 5 seconds before it stops? How far does the car travel during those 5 seconds before it stops, right? So I'm looking for how far, which I hope you guys realize is the displacement. Displacement, right? I'm looking for displacement, right? All right, so I seem to have everything, don't I? There's one more thing that I do know here that's implicit, which means it doesn't say it to me. It doesn't smack me in the face with it, but it's right here. It's in here, right? So I'm going to take a look at my equations, right? I'm going to look at my equations. Here they are. Which ones have displacement in them? Here's one right here. These don't. That's velocity. Here's acceleration. And this has final and initial and time. Here's one. Final velocity squared minus initial velocity squared over 2 times displacement d. But what's this? A. Do I know the acceleration here? What about this equation? Displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. That would work if I only knew the acceleration. Well, damn. Am I just boned? I can't do this because I don't know the acceleration? No, of course you know the acceleration. You can figure it out. Inside this right here, this little setup is the acceleration. You just got to find it. What is the acceleration? Acceleration is, and I'm going to look back on my formula chart, it's final velocity minus initial velocity divided by time. That's what acceleration is. Final velocity minus initial velocity divided by time, isn't it? Right? It's final minus initial divided by time, y'all. I know the acceleration. What's the final? 0 meters per second. What's the initial? 21 meters per second. What? Ooh, negative 21. What does that mean? It's going to be a negative number. Why? Because it's slowing down. Duh. Negative means opposite direction, slowing down. It's accelerating in the opposite direction. So what is 21 divide 5, right? That's my acceleration. So my acceleration is going to be negative 21 over 5, which is going to be a negative number. And guess what? I got my calculator here. I'm going to say negative 21 over 5. And that's going to show me, I'm going to divide. And it's going to say negative 4.2. I like decimals. Negative 4.2. So I've got an acceleration of negative 4.2. Negative 4.2. Now what can I do? Now I can go and I can find displacement, right? Now I can do that. So let's do that. I'm going to get rid of this stuff, right? Negative 4.2 is my acceleration. Remember that. Right? Negative 4.2 is the acceleration. And you should always be asking yourself, why is it negative? 4.2 meters per second squared. And this is meters per second. Yeah. All right, so now I've got all this. And you should be asking yourself, why is it negative? Well, it's slowing down. It's accelerating in the opposite direction, right? It's moving this way, but it's accelerating in the opposite. It's decelerating. So I know a lot of you guys, when you see that negative, you're like, oh my God, I did something wrong. No, you did something very right. So how far is my displacement? I'm looking for my displacement. Well, what equations can I use, right? What equations can I use? Let's go. Here's my equations. Oh, let's see. Can I use this one? Yup. Yup. Yup, I can. My displacement is equal to my initial velocity times time plus 1/2 at squared. I could also use this one. if I wanted to, right? This one would be a little bit trickier because I have to do math. I mean, Mathway does it for you, but this one has displacement on the left side of the equation, which means if I just multiply all these things together, I will get this. On this one, I have to put acceleration right here, negative 4.5, and then I have to move it around and stuff like that. So I'm just gonna use this one. So let's go. Let's do it. I like that. Let me write this displacement equation. My displacement is equal to my initial velocity times the time plus 1/2 times the change in time, right? Again. Oh, I forgot acceleration. Acceleration times change in time squared, right? Let me clean that up. You know that acceleration goes here. It's in the equation. It's in the equation. How do I know that? Because I got my formula chart. How are you going to know it? Because I'm going to give you the formula chart, always. Right? Let's see if I wrote it right. Displacement is equal to initial velocity times time plus 1/2 at squared. Yeah. Yep. Initial velocity times time plus 1/2 at squared. Love it. Now, all you have to do is plug and play. My displacement is equal, what is my initial velocity? 21. What is my time? 5. Plus, and this addresses like what happens before the acceleration, right? Before the deceleration, initial velocity times time. And it addresses what happens after it slows down. 1/2 times the acceleration is, and you can see that this is going to be negative because I introduced this negative 4.2. And then time is 5, right? Because it's slowing down over that time, and we've got to square that, right? So I got 21 times 5 plus 1/2 negative 4.2 times 5 squared. Guess where I put that in? My calculator. Let's go. You just put it in exactly like we did it, right? Time is 5 plus 1/2. And if you're not using parentheses, guys, you need to be using parentheses. That's the one way to make sure that the computer is doing exactly what you think it's going to be doing, right? Don't let it outsmart you. What is it? Negative 4.2, right? Is the acceleration? Let's check. Yeah, negative 4.2 times 5 squared, right? Times 5 and then square. Oop. And y'all know y'all got to put a little square, right? Boom, right there. So I got it. 21 times 5. That's initial velocity times time plus 1/2 times acceleration times time squared. It's just like that. Boom. If I get this, I simplify it. 52.5 meters. Wow, I did it. The displacement is found. I got it. So this should go in your answer. All right, what is the equation for uniform circular motion? Oh my goodness. Do you guys remember uniform circular motion? You should immediately, when something asks you for the formula, you're always going to have to be looking at this, y'all. What is, uniform circular motion? Here it is. Centripetal acceleration, right? Circular, centripetal, center pointing. We've got all that worked out. You got to know that whenever I'm doing something in a circle, right, a couple things happen. One, let's say this is like a ball swinging around, right? Maybe it's swinging around a pole. A couple things. One, its velocity points out like this, right? And I'm assuming it's moving this way. It's going clockwise, right? Its velocity points out, right? So I'm going to write that here. Its velocity points out. Its velocity. And we call this the tangential velocity because it's tangent to the circle, right? And then we have the acceleration. And guess where the acceleration points? Well, its velocity wants to go out and it wants to keep going, but something is driving it towards the center. That's the acceleration. It is centripetal, center pointing. When something points toward the center and it's changing toward the center every single second, it's going in a circle, dog. Wow. And this is the acceleration, bros. And we call it centripetal acceleration. Centripetal acceleration. So it actually was the formula for it. What is the formula to find centripetal acceleration? Well, all I have here is velocity and acceleration, and also this is called something, right? This is the radius of the circle, right? The radius of the circle. So let's look at my formula chart. It says centripetal acceleration is merely found by squaring the tangential velocity, that's v squared, divided by the radius, r. V squared over r. V squared over r. Centripetal acceleration is v squared over r. Let's go. Let's go. You're going to have to use that so many times. Now, back on that, right? This question asks, this car is moving, right, around this circle, around this turn in a clockwise function, right, like this. What is the direction of the acceleration of the car? Now, the car is moving around here, so, right, it's moving around here. It's moving this way. What direction is it accelerating? And if you say north, it's going forward. No, that's its velocity. What way is it accelerating, right? Because it's changing its velocity by changing its direction. Towards what direction? East, towards the center. Is it always going to be east? No, don't be a fool. It's going to be whatever direction the center is, compared relative to where that car's at. So if it was right here, guess where the acceleration would point? This direction, right? And if it was right here, which way the acceleration would point? This direction. So it's not always going to be south or north or east. The correct answer is going to be it points towards the center, whatever direction that happens to be, right? If it's right here, it's this way, right? If it's right here, it's this way, so on and so forth. The acceleration is center pointing, right? Let's go. Oh, how about this one? A train is moving at their... I explained that one right there. I don't need to go through that one. That's relative motion, right? You got to look at how fast things are going relative to each other. Both of those are relative motion. Check them out. Okay, how about this one? Gravity depends on which two features? Gravity depends on which two features? Isaac Newton figured this out, right? Isaac Newton figured this out. He called it universal gravitation. Now, here's a trick. If you're ever confused about a question and you just don't know what's going on, a good place to start, besides annotating the problem and underlining it, circling things, a good place to start is look at your formula sheet. Where is universal gravitation? Here it is. Force of gravitation between two objects. Here it is. It equals universal gravitational constant times the first mass, the mass of the first object, times the second mass, divided by the distance between the centers of the objects squared. There it is. The force of gravity is equal to big G, the gravitational constant, times mass 1 times mass 2, divided by distance squared. And the answer is actually in that equation. What two things did Isaac Newton figure out matter? Right? Well, we have big G, which is the constant. It's never going to change. But all gravity depends on two things. How big things are, their masses compared, and those are directly proportional, and indirectly proportional to how far apart they are. So M is mass, right? And guess what D is? Of course, that's distance or displacement. So these two things are in the equation. These two things are the things that matter. Those are the variables that determine something's gravitational attraction to another thing. So, what happens if I double the distance between these two things? Well, let's go back to my equation, right? If I double the distance between two things, right? So I'm looking at the distance if I double it, right? Which means if doubling the distance means if it's like 1 mile apart, now it's 2 miles apart. Do you think the force of gravity is going to get weaker or stronger? You should say weaker, right? Duh. If I move something further apart, it's going to be less attracted, right? Not more. And this equation tells us that, right? So if I'm dividing by the distance, what is dividing by 1 squared? Let's do that. Whatever this is, this is the force, whatever, don't worry about that. Let's divide by 1 squared, right? What is 1 squared? 1 squared is 1, so I'm dividing by 1. Does that change anything? No. But what about if I am dividing my force, whatever this is, don't worry about it. Divide by, what if I double that distance to 2? What is 2 squared? I'm dividing by 4. I'm dividing by 4. If I double the distance, guess what? Force goes down by a factor of 4. It goes down by a quarter. That pizza gets divided in 4. How did it go from 2 to 4? The squared. It's right there, the squared. 2 squared is 4. What if I triple the distance? It goes down by, guess what? I hope you say 9, because 3 squared, 3 times 3 is 9, and so on and so forth. 4, 9. Oh, it's a inverse squared relationship. It's an inverse squared relationship. So here's some calculations. I walk you through that. All you have to do is input. There's mass 1, there's mass 2. Multiply it by the gravitational constant, big G, which is always the same, by the way. Big G is always 6.67 times 10 to the negative 11. Terribly small number. And again, that is found in the constants. There's my constants. There it is. There's big G. Not to be confused with small g, which is the acceleration due to gravity on Earth, 9.8 meters per second, or meters per second squared. But big G, the universal gravitational constant, 6.67 times 10 to the negative 11. Get it while you can. All right. How about this one? This diagram shows a 4-kilogram object accelerating at 10 meters a second squared on a rough horizontal surface. And it asks, what's the magnitude of the friction force on the object? Wow, look at this damn question. This is so tough. How will we ever do this? I got to figure this out, y'all. What in the heck? Let's draw it. That's what I want you guys to get in the habit of, is this. If you're given a problem with what these free body diagrams, as we know they are, free body diagrams, if we're given a problem with these free body diagrams, we have to draw it. We can't just like imagine it in our heads. So a free body diagram starts with a box, right? So our box is a 4-kilogram object. Who cares what it is? It could be a dog, it could be a roller skate. I don't care. But its mass is 4 kilograms, and that is going to play a huge role, right? Why? Because Newton's laws say that force is equal to mass times acceleration. And mass is in the formula. So let's draw the forces on it. All right. So it has an applied force of 50 newtons. All right. So something's pulling it, right, or pushing it at 50 newtons, and then friction is holding it back, right? It's like got a rough surface, like. But this one is bigger than this one, right? All right. How do I know? Because it's moving, right? It's moving. How do I know it's moving? Because it's accelerating. It tells me it's accelerating at 10 meters per second squared. So the applied force is 50 newtons, and the frictional force is unknown. I don't know it, right? I don't know it. And I hope you've read this question before. So the frictional force is unknown, and the applied force, right? So let's call it the force that's applied is 50 newtons, right? Something's pulling at it at 50 newtons. And the friction force is unknown. So what is the force of friction? Oh my goodness, how am I ever supposed to figure that out? Well, there's another piece of information. It says this box is accelerating to the right at 10 meters per second squared, right? It's scooting along at an acceleration of 10 meters per second squared. Every single second, it's going 10 meters per second faster. How is it doing that? Because this force is winning over friction, right? So how can I figure out what the overall force is? What the overall force is? Or the net force, right? Force net. All I have to do is multiply the mass times the acceleration. Let's do that. Force is equal to mass, which is 4 kilograms, times the acceleration, which is 10. Force is equal to 10 times 40, y'all. That's the mass times the acceleration. All right, how many newtons of force is it? You should see that 4 times 10 is what? 40. 40 newtons. So the force on this, right? The net force on this is 40. The net force is 40 newtons. But you're probably like, wait, what are you talking about? It's 50. Well, think about it, dude. 50 newtons of force is dragging it this way. What's holding it back? Some newtons of force. What do you think this is? How many newtons of friction do you think it's holding it back? How many? Think about it. Think about it hard. What does it have to be? The outcome is 40. This is predetermined, right? I know that the net force is 40. What does this have to be? I hope you say 10 because you'd be right. Think about it. 50 newtons pulls this way. Friction is pulling this way by 10. Which one wins? This one. The pull wins. But I have to subtract all this, right? So this is a vector, right? This is in the positive direction. This is in the negative direction. I can say that's negative 10. This is positive 50. If I add those two together, right, I'm really subtracting those numbers. If I'm adding this negative number, that's 50 minus 10. That's 40, right? How did I do this? Well, I used Newton's equation, right? And I did this two-step process where I figured out that if it's accelerating, right, at 10 meters a second, and its mass is 4, I know the net force on it is 40 newtons. And it's 40 newtons by this pull of 50, but I have to subtract the 10 that it's being slowed down by because of friction, right? Let's go. Those are free body diagrams. You're going to see them. Ooh, how about this one? A 12-kilogram bucket of water is hanging motionless at the top of the well, right? A 12-kilogram bucket of water is hanging motionless at the top of a well. Let's draw that. We got to draw these, man. You got to get into this habit. Don't just let me do it. Get out your pen and paper and start drawing these out, man. This is how you're going to do it. So here's that bucket at the top of the well, right? It's hanging motionless, right? And it might have water in it. And the mass is what? The mass is 12 kilograms. The mass is 12 kilograms, right? So what does it ask for? What is the tension force in the rope holding the bucket? What is the tension force, right? So let's do a free body diagram of this, right? So first of all, we got to see that this bucket of water is hanging motionless. Motionless. They're going to tell you that. Motionless. And that means something. It's huge. That means that there is no net force acting on it. Everything adds up to 0. If there was a net force on it, it'd be accelerating in that direction. It'd be going up or down or left or right. But it's hanging motionless. So what forces are acting on it? Remember, every action has an equal and opposite reaction, so we have to have some forces here. So what do you think is pulling down? If you say gravity, you're right, duh. And that's its weight. That's the weight of the bucket. That's the weight of the bucket, right? So that's the weight of the bucket. And I'm going to label that. So F of the weight of the bucket, right? And there's an equal and opposite reaction going on here. And it's pulling up, right? Equal and opposite. And that's the tension force. And that's the tension force. Let's go. Oh, shoot. I'm trying to draw with arrows. I'm a stupid. That's the tension force, or F sub T, right? So these have to be the same, right? This and this are the same because it's motionless. If I add this, this is going to be negative and this is going to be positive, right? Remember, physics, negative just means opposite direction. So what is the tension force? What is the weight force? It's the same because it's motionless. Well, how do I figure that out? It doesn't give me any numbers. It gives me the mass of this is 12. Well, this is why I taught you Newton's laws, ladies and gentlemen. Newton's second law states that force is equal to mass times acceleration. So the weight force, weight is a force. The weight force is equal to the object's mass times its acceleration. So let's find out. What's its mass? 12 times what's its acceleration? Oh, you guys should know. On Earth, you're always accelerating towards the ground at negative 9.8 meters per second squared. All you have to do is multiply those numbers, dog. What is 12 times 9.8 in the negative? Let's go. 12 times negative 9.8. And it's going to tell me. That's going to be negative 117, or about negative 118. So 118 going down. 118 newtons pulling down. Newtons. Down. So if this is 118 newtons down, what does this got to be? 118 newtons up. Why is it the same? Equal and opposite reactions, bro. Right? If the rope wasn't strong enough, it would break, and guess what? There would be no more tension force. Guess what I'd be doing? Going down, homie. I'd be falling. There would be a net force of 118 newtons going down, bro. Down. Let's go. How about this one? What's the magnitude of the normal force acting on a 10-kilogram object laying on the ground? That's a very similar question. So we're on that last question of the quick check. What is the magnitude of the normal force? Well, to understand this question, you had to have paid attention to the lecture and realized that the normal force is a type of force, right? It's a type of force that everything that's not falling is experiencing, right? Everything is being pulled down, but if you're not falling, you're resting on something. And since every action has an equal and opposite reaction, it's pushing back, right, against gravity. So let's see that. So if you're sitting on a couch right now, right, gravity's pulling you down, but that couch is pushing back up on you, right? And we can draw those vectors, right? So here's the force of gravity. We call it your weight, right? It's a force. But then the couch is pushing back up on your booty, right? And we call that the normal force. The normal force. Why do we call it the normal force? Why is it normal? Because it's everywhere, bro. It's normal to have. It's normal force, bro. F sub N, the normal force. F sub W, the weight, right, due to gravity. And here's the mass of an object, and it tells me the mass is what? 10 kilograms, 10 kilos, right there. So how do I figure out these? Well, you know they're the same, right? They're the same. It's sitting on the ground. It's not falling. So there's no net force. Net force is 0. You might say that net force is 0. So that means that this one's negative and this one's positive, and they're the same number because they're going to add up to 0. So, but what is that force? Well, let's figure out how much this sucker weighs first. Your weight force is equal to mass times acceleration. Your weight force is equal to the mass times 10 times what's the acceleration going down? You got to know that it's 9.8 in the negative, right? What is 10 times negative 9.8, right? Come on now. Negative 98. Let's go. Let's go. So what's this one got to be? Positive 98. Come on. What's positive and negative? Same number added together. 0. That means it's motionless. Just chilling there. Sitting there. Let's go. You need to know these. You need to know how to do these. I'm glad you stuck with me. Everyone should get 100 on this bad boy. And then go and work on your quick check. We're learning all new stuff this week, including work, energy, and power. Fun stuff. All right, get to it. Love you guys. Bye.